Hello, thank you to everyone attending today. We're the University of Wisconsin-Madison team, the Solar Saviors, and this is our resilient microgrid for the Pacific Northwest National Laboratory. Next slide. The Pacific Northwest National Laboratory will be referred to as the PNNL throughout this presentation. And this is a Department of Energy facility in Richland, Washington. The PNNL conducts state-of-the-art research experiments daily, so energy resilience is a high priority for them. When the main grid experiences an outage, it costs them data, lost productivity, and a loss of money. So our main objective was really providing them with a combined PV and battery system to provide the PNL campus with a resilient microgrid. Next slide. So now I'll just review some of our team structure and work effort. We are 4 mechanical engineering students at the University of Wisconsin-Madison, and we heard about the Solar District Cup in our senior design class, and we chose it as our project for the year. And for the competition, we each specialized in a specific area. Next slide. Shown on this slide. And we'll get into each of our specific areas throughout this presentation. But each of us, even though we specialized in one area, we kind of collaborated and advised one another along the way throughout the competition. And now to get into more of our proposed system design, Greg will start discussing our solar plus storage design for the PNL campus.
Greg, I think you're muted.
I was muted. Okay, yep. So before we could really start designing, we didn't have an understanding of what the energy consumption of the campus looked like. And they gave us some data to start with. So we might have had something that started with a month that looked like this. And the thing was that the data was relatively incomplete. And there may have been a large gap in October. And if we looked at a building with a similar time frame, it had completely different gaps. Or there were buildings that even just have completely different data. So that was kind of well, what do we do with all this incomplete data before to design the system? So what we did is we basically kind of leveraged a Python program to perform the thousands of calculations to try and fill in the gaps and help us get a simulated realistic year of data. And basically that kind of gave us these 3 things. They're kind of data sets, building specific data is building specific data, or building specific energy consumption, probabilities of occurrence is based on the ways that the buildings and energy consumption was categorized. It's what's the probability that this certain type of categorized day will happen. And then the representative day is what is the most characteristic day of this type of days. And really at the bottom line, what these things are made up of are standard deviations, averages, maximums, and some subtraction for comparisons. And basically once we had these 3 data sets through looking at the data they gave us, we were able to put this through a random number generator. And that was able to give us a complete full year of hourly energy data for every building. That was a really great foundation to start designing the system off of. And obviously as we go in to add this battery and PV system, there's a lot of extra variables that we need to consider. Solar system size, battery size, C rates, efficiencies, all that good stuff. And really we were trying to get to somewhere where we could see the battery charge for every time step of the year, how reliable is the system, and how are we meeting those critical loads, and how much extra energy can we provide to campus. And that's a lot of variables for us to change on our own. So we took a similar approach to filling in the energy consumption data, and we kind of leveraged another Python model that we created to try and have it to where you could put in the inputs on the left, it would go through the Python model, and we'd get the things on the right. And then we would be able to basically go back in, change the input slightly, and move forward. And basically, we were able to do this with this library in Python called SciPy. And basically, you can give it this thing called an objective function, and that characterizes your system in some way. We decided to characterize the system on the terms of costs because that's the most understandable metric that we're really going to be providing, or we would provide to a client. So we kind of kept it in that regime. And looking at that, there were a couple key costs. So the solar system cost was one of the main things. And this really just depended on the size of the solar system because things like the type of panel selected were kind of fixed. We have the battery system costs. There are things like C rates and efficiencies that go into that, but we chose a lithium ion chemistry, so that was kind of fixed. But so really this is just how big the battery is. And then we kind of did an approach to reliability, and we really wanted to focus on that. So we had a cost for like not having reliability and say that the PN know how to black out, we essentially said that it would take like 10% of the staff to a couple of days to like get that back and running. And then we also have like the miscellaneous developer fees and whatnot that we also had to deal with. So basically through pushing it through the subjective function, it reiterated on those inputs and we were able to get to like an optimized system based on the costs and our other assumptions. And what we got to is a 2.9 megawatt AC solar system, which is localized in the southern field because we're able to take advantage of the distribution network. And then we were using two lithium ion batteries, a 6.5 megawatt hour battery on the main part of campus where the critical loads are highest. And then we have a smaller 2 megawatt hour battery on the northern part of campus where critical loads are a little bit smaller. Looking a little bit further into that solar system, there are about 7,100 solar panels arranged in these subarrays that we were able to play around with to get them to like our shading and whatnot. We picked a very standard commercial solar panel for our relatively large installation. And as a result of that, we also picked a larger capacity inverter. And moving into this, we're going to talk into like some of the expected performance and operation of the system as well. So we were able to produce 13% of like the annual energy offset for the PNNL. And through like iterating the solar panel placement on the field and orientations, we were able to get to 3.9% shading loss, which is within that like 3 to 4% industry standard that we were finding online. And then the main thing to really think about with the battery here is this like right column, which is reliability and 24-hour reliability. The reliability is the chance that if there was a blackout at any time, we'd have a full ride out through the blackout. So 100% of the time steps we can make that happen. And we wanted to make it a little more robust. So we made it like 24-hour reliability, which is like 24 hours after the blackout. If there's another blackout, what are the chances that we could support that again? And we have an 85.2% chance to do that. And then just a little bit of operation. So the PV system is really there to like mainly charge the batteries to 50%. So that's like, it's best for the health of the lithium ion chemistry, helps us last 25, 30 years. And also it helps us just ride our critical loads. We also have like supplying critical loads is a really key thing, supplying it from the batteries mostly, and maybe there will be some PV or supply. And then we also have energy offset, which is mainly like pushed through the PV system, and the batteries will provide some energy offset, although the solar system isn't quite sized for like excess energy offset. And with that, I'll move to distribution system with Lauren.
Awesome. So whenever you're interconnecting PV generation to the grid, there's always some distribution risks. And I'll get into discussing some of those. So hosting capacity is the amount of PV that can be interconnected without changing the existing infrastructure or wearing out the equipment. So on the heat map that we were provided, each interconnection point had a specified location and hosting capacity. And PV size up to this capacity can really be interconnected pretty easily. But if PV is sort of larger than this hosting capacity, it'll require additional devices and finances with bigger PV size. Next slide. So when we started really looking at the heat map, we noticed that there's sort of a one-line diagram showing the distribution network, and we found that there was a branching in the one-line diagram. So we noticed the network connects together further downstream from the main campus and the PV system location. So we chose two interconnection points very close to our PV system, but these points were on separate branches of the hosting of the distribution network. So our PV generation was actually split between 2 points. So less PV was connecting to each point compared to only one connection point, which allowed us to have a larger PV system size. And this also created better power flow. So one branch is not limited by the other branch. Next slide. Another violation that we really wanted to consider was the risk of overvoltage and undervoltage. And this really depends on the distance between the campus interconnection point and the PV system size, as well as the transportation voltage and the location of the buildings that the power will be supplied to. So there's an acceptable voltage range provided by the utilities, which I showed in the slide with like a green arrow. Next slide. And buildings too close to the interconnection point will have a higher probability of an overvoltage violation, and buildings too far from the interconnection point will have a higher probability of an undervoltage violation. Next slide. And one device that can sort of mitigate these violations is a voltage regulator. And they can reduce over and under voltage violations and increase the distribution's hosting capacity. So we decided to add this device into our distribution network as well. Next slide. Another consideration or risk when interconnecting is thermal overloads. The larger the PV system size, and I guess if you're only connecting to one interconnection point, this would be more of a risk as well. It's basically an overcurrent causing a thermal overload, but there are also devices to mitigate these violations as well, listed on the slide. Next slide. So when connecting to these interconnection points, these systems aren't really designed to intake power from multiple sources. So there's risk of reverse power flow back onto our transmission system. However, our PV does utilize smart inverters, which increase hosting capacity because these can be programmed with various control modes listed on the slide. And these can be programmed to protect the distribution system from reverse power flow by shutting off electric flow when the grid is unstable or backflow occurs. Next slide. Fabio will now review some of our financials for our proposal.
So yeah, I'm just going to provide a quick rundown of the financial outputs of our system. Okay, so we'll start with the photovoltaic system. So as you can see, our construction cost was set to $1.63 per watt AC. This was based on past costs for similar size systems and price tendencies. So the price has been reducing over the years. Our estimated annual production will be around 4 million kilowatt hours. And with these inputs, we're able to set our PPA price to $0.082 per kilowatt hour, which lays within market expectations, which was something we were aiming for. With this system, the internal rate of return will be around 5.56%, which is very similar to the hurdle rate, providing the net present value to be as close to zero as was demanded by the competition. Our annual electric savings on year one will be around $167,000, and the total cash flow over the lifetime of the system will be around $2 million. Next slide, please. Now, talking a little bit more about the solar plus storage unit. So our energy storage system costs will be $400 per kilowatt hours. Again, this was based on past system costs for similar size systems and the price tendency over the years. It was also based on the C rate, and this was actually one of the ways we were able to decrease costs and increase profitability by changing the C rate of the battery. Our demand reduction will be 789 kilowatts, and the PPA price set for this system is 11 cents per kilowatt hour AC. Ultimately, the annual electric savings will start at $219,000, and the total cash flow over 30 years will be around $2,800,000. Next slide, please. Thanks. So this slide just kind of breaks down each system characteristics. So we have the PV system and the battery storage unit. The main point of this slide is the column on the right. So with our battery storage system, we were able to increase the total cash flow by around $800,000. Now, how much is this going to cost? So this slide provides a breakdown of the costs and the incentives. So we have the ITC and the max and each system separately. Ultimately, what our client is looking for is the last two rows, the total project cost before incentives, which is around $9 million, and the total project cost after these incentives, which is around $5 million. Lauren will talk a bit more about the development plans now. Thank you.
Okay, so the first thing that we wanted to do within the development plan was figuring out where we wanted to place the system. So we started by looking at the Google map file that was provided by the competition, and we saw that space wasn't really an issue. So we kind of had to start by eliminating places instead of finding places. So the first thing we looked at was land use considerations, and those things included slope of the land, the soil, the surrounding wildlife. Next slide. And then from there, we went into zoning ordinances, and this gets a little bit challenging with the permitting just because the PNNL is a nationally or a federally owned lab, but it falls on state land. So it just gets a little bit challenging making sure that we apply to the right jurisdictions when we do get into permitting. Next slide. And then finally, like Lauren mentioned, we wanted to have somewhere that was close to interconnection points so we could connect easily to the existing grid. Next slide. So with that being said, this is our final site location. Greg kind of already talked about it. It's just south of the main campus, just split into two fields. Next slide. You can go right to the end of the timeline. This is just a rough construction timeline. We had about 8 months. So like I said, applying for permits is going to be a little bit more nuanced just because of the jurisdiction. So we wanted to start that as soon as possible, as well as ordering all the equipment so we can get it into a safe and dry place in time to be constructing and assembling all of the panels, which we'll be doing in months 2 through 7. And then the final month will be left for inspection and interconnection. Next slide. So this is just a quick overall summary slide. We just wanted to highlight that resiliency was the most important thing to the PNNL. Like Greg was mentioning, with over 100% reliability after, or for an initial blackout, and then 85% after 24 hours. And that allows continual experimental progress, which is really important to the PNNL because they have ongoing experiments, and losing data can cost money. And of course, sustainable
Sorry, Lauren,
energy.
I have to cut you off.
That's okay.
We're out of time.